All right, I believe we are live. Let's just see dashboard right here. Content, live. Should have done the trick. Stop streaming. Let's see if we can do it like this. Got later live, no. Later streaming software. Let's try that. Schedule stream. I am okay. Your channel. Day one learning saw. That's exactly what I want. So, like this. Okay, cool. I think this is the link. Matter of fact, let me just go send it on this over here, just because it's like sensitive information. Boom. YouTube Studio. Content. Live. Here we go. Right here. Day one self-learning. Let's take this live link. Let's copy it over here. Copy video link. Gmail. Compose. Send this to myself. Live link. Let's see if this works. Live link. Cool. So we got the link. Let's see if we can try this again. Give me the live link, copy video link, and paste right here, send. I'm just checking if the stream's working. Like, I don't know who I'm talking to. There's literally nobody in the stream. I just gotta practice, you feel me? Let's try it right here. Okay. Yeah, okay, looks like it's working. Let's send this out really fast.
I'm taking punch. I'm taking prime check.
That's a story. Let's make a story right here. That's a story. I don't know, give me a template here. No, we'll just do one of these. We'll take a picture, how about that? I like that. Yeah, that's a good idea. So right here, OBS like this. It's a good picture. Going live for the first time. Going live for the first time. Here's the live link. Here's the live link. Going live for the first time. Session 1. Going live for the first time. Day one learning. Going live for the first time. Day one of rocket science. My YouTube. Let's see if it shows up like that. That's probably a better idea. Let's use this right here, your channel, Rom A Loca. We'll try that. Rom A Loca. let's do it like this. I like this. Okay. At Rame Luca, going live day one of my rocket science on my YouTube. At Rame Luca. And then I'll put an emoji because it's my bare minimum level of marketing that I gotta do here. So here we go. My story. Yeah, I would like it to go on my story. Did I just post it? Going live day one of rocket science on my YouTube. I'll probably put the link here in my bio, my Instagram bio. Yeah, that seems like a good idea. Let's see, edit profile. I mean, it really should be live. Like you can probably enter if. Yeah, it looks public here. I'll put the link here. Is there a link? An external link. There's a lot of work, man. Let's see here, ROM. Got one person watching too. I'll put the link. Okay, so let's get it started. So I'm using two different laptops here. I don't want this going. Let's see. It's not what I want to do. Okay, let's just get to it. So this isn't really structured. I got this Google Doc open right here. We're gonna literally just go step by step here. I did see an interesting video right here where it's just like how to learn hard things. It's just like a YouTube video right here. It's not this. Here, we'll go to YouTube. Forget about it. So we're gonna do this like literally step by step. So what are the skills that aren't? Let's go right here. Basically that video that I was talking about, it's like, it basically says it's an old video. Like I'm talking 13 videos or 13 years old. And the guy talks about, how the best way to learn like really hard skills is to just like have a very solid foundation in the fundamentals. So I think that is like obviously the first step. There's going to be a huge learning curve. So this is kind of how we're going to go about it, but gas laws. So core theoretical foundations, I understand that. So, I mean, obviously, classical mechanics seems like you have to have a solid basis in physics, no doubt. Fluid dynamics, electromagnetism, yeah, obviously. So these are all skills that, I mean, I remember back when I was in school. I mean, those were like kind of like the last times I touched those things, but. So these are like really, really fundamental. So I'm gonna go to the math. So I also gotta be very clear here. Here's another thing. What do I want to tangibly do with rocket science? It's kind of easy to just say like I learned rocket science. Also a second goal here is, I'm also building product right here. And I intend on like when I'm not live streaming having like functional versions of agents working to help me learn. Let's see what we're going. Daniel Shuey accepts it. Agents working. Let me learn. So, I mean, the best way. So here's one thing. We'll quickly wrap up this. We'll just read this prompt all the way through, and we'll be a little bit more specific. I think this is just too easy of a prompt. Let's be very specific. Rocket science. Let's spell that right. I want to learn the skills necessary to here. That's actually an even better prompt. So, what are some applicable things that a self-learner can do when they're using applications? I always find it funny how GPTs very much, they're always like agreeing with you, like, yes, absolutely. It's always that. So let's see what we got here. Simulate before you build. So yeah, simulations is honestly where my head was going. So we'll just get some ideas here. What do I want to tangibly do with rocket science? Let's go like this. Simulations. I also thought, like, I mean, it's literally rocket science for a reason. What do you do with rocket science but build a rocket? So build. I'm not gonna, you know, I don't have the funds to build a rocket at the moment, obviously, but build something rocket adjacent. How about that? Like, obviously affordable. Obviously, an extremely. Let me spell that. Did I even spell that right? Extremely bassy version. Not did I? Is that even a bassy version of a? I guess you could call it a projectile, right? That's not even spelling. Extremely basic version of a projectile. Apply. I mean, it's all applications. What am I talking about? Let's go up here. Applications. Simulation build something, obviously extreme. That being said, okay, so we'll really refine the goals here. I mean, you know what? We could just do it now too. Like, I don't know what else I'd be doing. And my mom's ruthless. I posted a reel yesterday, and she was clowning me because I had my mic with my stand, and she was just like, next time just attach the stand, son. Like, trust me, it's not that hard. So she's my family's absolutely giving me a hard time. I love it. That's funny. Let me give him some
announcement today. Which topic will I be learning? Right here we got quantum mechanics, rocket science, string theory, reinforcement learning, general relativity, and thermodynamics. So okay, let's choose one at random here. Oh.
I love that. I really, you know, I'm not the influencer type, man. That's it's a very I don't know. I'm not comfortable doing that. So it's kind of fun. It's really fun, actually. Like, it's kind of nerve-wracking too, cause like, I don't know. I'm not the influencer type. So like, putting myself out there, it's an uncomfortable thing. So let me get back. Let me get back here. We derive Newton's law for it. Jeez. See, I don't even know what that means. Compute delta V for Moon or Mars transfers using orbital mechanics formulas. Okay, great. Let me just look for something here. Yeah, computational tools to learn. Open rocket. Kind of seems interesting. So the reason I'm doing this is because I kind of just want like a very tangible goal that I'm working towards here. Yeah, CubeSats. I've heard of CubeSats. It's basically like a very affordable. Matter of fact, it's actually a really interesting idea. CubeSats, not too affordable, I will say, but I always wonder. Wait, let me just see something. Is it Command Enter? Nope, not that. Shift Enter? It's not Shift Enter. Option back. Man, I don't even know, man. I'm also just learning how to indent back in Google Docs. Keyboard shortcut. For Windows, press Command. Whoa, is that really the case? Let's see, Command. Yeah, it is. Okay, good. I don't know. I keep scrolling for the top chat because I'm looking at my chat. I'm like, is there even anything? It's kind of comfy when there's nobody. Like, I'm just kind of speaking out loud, maybe thinking out loud. So let's build model rockets. Yes, that's the goal. Build flight computers. See, that's really interesting to me because my background, like I said, is kind of mathy, CS version, something like that. So we got something fun here. So, I mean, instead of using ChatGPT for that, what? Some real world applications. I mean, let's see what we got. Satellite launches. This is another GPT. So, I mean, I really think this is like two in the air. Literally, the first thing I want to do is build something rocket adjacent. It's rocket science for a reason. So let's just call that the goal. Now back to our prompt. It's also here's another thing that I wanted to mention. Like part of what I'm trying to build. These are two prompts, okay? Like as I go more and more into this, I mean, you can see right here, that's like a whole lot of disorganization, I feel. I'm using ChatGPT. You can do a lot of everything, really. And I mean, they did make efforts here to make projects and like kind of give you the opportunity to organize. And here's a really interesting one. Like, you know, you have the ability to work your way to be nudged through your problems. So that's really interesting, actually. I think that is a very key feature of just actually building some backing. So here we have. I mean, what do you want to do? Obviously, this is really key here. We'll just make it real simple and just make it simple. Like this is exactly what's going on here. So let's just is anybody tuned in? I am curious if this is getting any motion. No, please do not play that video. I have this stupid little video that it's like my default, when I search up YouTube, that's just kind of like what I have. Let's see if we got any lives here. Let's mute on this, that's best. So that's not at all what I wanted to do. Good. Build something rocket adjacent. So let's just let's stick to this. I wonder what this is capturing. I don't know if the OBS is capturing anything funny about my place. We got the books over there. That's okay. Okay, we're safe. I'm just back. I don't know if I post something extremely worldly or something confidential. I don't want to put out into the world. Like that's why that's another one of my worries. I'm just like, am I posting something? So, anyways, let's get back to something like this. Let's just ask it a very directed prompt. So, where are we? Rocket science, right? Yeah. Let's go here. Matter of fact, can we move this? Let's move this into rocket science. It won't let me do that. Move to project rocket science. Boom. Okay. What are fundamental skills? Well, we'll even say, imagine you are a professional rocket scientist that knows. Why did I spell that wrong? Yeah, that's good. Rocket scientist that knows how to prove or to actually make very basic projectiles. I don't even know if I'm using the right terminology. Make very basic projectiles that if I am a self-beginner. I am a self-learner in rocket science. Which skills would you recommend that I learn in order to make a basic rocket? How about something like that? Took longer for a better answer. Okay, good. Newtonian mechanics, we got it. Calculus basics, okay, aerodynamics. Yeah, that's honestly good. So I mean we have our most basic. So let's find out what math do you need to know. I always heard, yeah, what math do you need to know? Because So I don't really see any Lineal. So no Lineal. That's okay with me. So yeah, okay. So what even, you know, here, let me just see this. MIT OpenCourseWare is actually a pretty great source. So here's the strategy here. I want to prove that with the state of, or with the tools at our disposal, I'm talking like whatever, our LLMs and all of that, like what can you actually, or how efficiently can you learn these new topics? So let's just see if they got stuff like here, the aerospace dynamics, aerospace engineering and design. I think that's an important. Second right here. Go. I'm gonna quickly. I need to do some stuff. I just got a crazy message right there. I don't know. It feels like people are so curious about your life after you put yourself out there. They're just like people I don't even know. I think that's hilarious. Let's not do that. So big picture goal. Small model rockets they use commercially. Sure. Yeah. Newtonian mechanics. You know, this is tough. I was always so chopped at mechanics, but it's important. Okay, so let's go. We're gonna do that. Let's. I mean, probably MIT OpenCourseware has something great, right? Physics 1A. That's what it's called at Berkeley. I don't need to learn quantum. I don't need to learn classic mechanics. That looks just like what I'm interested in. There's a guy named Walter Lewin. Let's just go right to the readings. How about that? So they got lecture notes, assignments. I need an assignment. Force and vectors. Okay, good. This is something I could definitely use. I'm gonna do myself a favor. I'm gonna go also do this. Dynamics, MIT, OpenCourseware. I think this is an interesting. Oh, we have it. Lecture notes, assignments. Right to the assignments. We need applications only. Kinematics. Geesh. You know what? Let's start here. Quite frankly, let's. We're gonna highlight a very important thing. I actually tried self-learning a lot of topics like this, just like going straight to the hard stuff and just breaking it down from there. But let's go right here. I'm gonna actually just gonna do this over here. So. We got it right here. Exams. I do need problem sets. That's exactly what I need. So I'm gonna send this. Let's just open it up like this. Just download the file. Cool. All right. In this problem, consider a long duct of height 2h as shown below. I'm gonna go ahead and grab my iPad one. I can just like write on it. Cool. Let me just grab my. Start off, come on, yes. That's hilarious. Apple Pencil, 0% charge. Actually, let me also grab that charger. Let's see, got it right here. Let's charge this up. The reason I got that is I just want to write this down. I don't know, taking notes is so cool, but sometimes you just need that pencil paper. Like I'm talking like on Google Docs or something. It's honestly preference, but okay. So check it out right here. This is the single screen. I have a much bigger screen here, but we'll just try to do it on the one screen. I'll try to get twos later. So in this problem, consider a long duct height of apparently the live stream is difficult to find. Is that so? Rame Hiloka. Interesting. Let me send this link over. I can send the link over. That's hilarious. My buddy Shervin, he's like an old connection. He's at the startup Kuba. I should maybe specify that the startup is very the features are ironing out. I have like functional versions are going to be built like through CLI, and then the goal is, the thing about it is like, yes, I'm going to be probably using agentic, but man, is that expensive. So I mean, honestly, the goal is a raise. So I'm talking demo world is on my radar. Demo and interest. That's kind of what I'm looking for right now. Let me see if I can send it to her. Oh yeah, like right here. I get an interested viewer. I'm really excited about that. So cool. Let me go like this. Gmail. Right here. Bang. To market. Let's copy that link. Yes, copy. Control V. The desktop I'm recording on is Apple. The one that I'm doing all this other stuff is plugged into Windows. So like my command key is whatever, my copy and paste, it feels whenever I'm doing the keyboard shortcut. That's weird. So anyways, right here. Where is it? So okay, so my idea is right here. Let's go in this problem. Consider a long duct of height 2h as shown below. So look, me as a complete novice, I look at this and I am immediately lost, right? So I mean, a very nice first instinct and like a very like kind of like a privilege that we're handed is we can just hit one of these right here. I don't think there's like I'm not sure if there's a screenshot feature, but here we go. We assume that the other velocity components are 0. And matter of fact, there's an interesting feature. I honestly have tried it. I think kind of like what's going on here is I plan on doing something really cool with this feature, or kind of like, you know, making this feature very conducive to actually like doing some real work. I'm not talking about just like loading up courses and stuff. I think we're afforded the ability where we can just kind of do this open-ended. I'm pretty sure like all LLMs talk about, or all LLM companies are talking about, like one of their metrics is, we can do PhD math level questions, like we can solve problems on the IMO and stuff. So it does seem like, I mean, also the company I'm thinking about, you can just like screenshot things and just get like pretty open-ended responses. Of course there's going to be like hallucinations and whatnot, but okay, so here we go. Let's actually just upload the PDF, right? Let's just see if we can do one of these. Download. Sure, just save it like that. We'll go like right here, and then we'll add this. Something like that, right? This is just I think I'm just kind of like proving a point. Okay, so in the file above, please explain what I need to, how to solve, right? How to solve problem 1. So let's see if it allows me to think. Okay, thinking better for a long word. Let's actually take a look at this thing, because it just looks like gibberish. Let's go. Sort of long duct of height 2h. Let's get my paper out here. And let's also do this while we're at it. Let's go with like a terminal, please. Yes. Great, great. Can we do one of these? Clear, great. CD. Wait, where are we? Let me just, okay, CD desktop. CD desktop. I'm pretty sure it's McNair Rocket Science. Yeah. Or CD Rocket Science, right? Great, LS, no. Code. Actually, I think we'll just leave this for our CLI programs. I plan on making some fun agents in that later, but let's see if this. Okay, so the setup we're given right here, right? Now see, we're in a long 2D duct of height h and velocity fields in the form. So here, off the rip, I am reading this, I don't know, maybe I don't know what so many of these definitions are. Like I'm talking duct, like what is a duct, you know? What is a velocity field? What is, I don't even know how to pronounce that. Uniform Kuwait. I feel like I'd say a bad word if I tried that one. Okay. 2D duct of height h with the velocity fields of the form. So immediately, let's start here. What is a duct? We dive deeper, yeah. Like, as a matter of fact, we should specify. I mean, I know what it. Okay, so the channel is open on top. Okay, makes sense. Flowing along 2D duct of height h. Very long in the x direction. So let me get out my trusty little. Just go to Notability. We love Notability. Accept. Okay, we accept it. We're gonna go new. New. All right, let's just start ripping. So, the duct is very long in the x direction, so ignore entrance/exit effects. Okay, understood. I believe the top and bottom walls are flat, separated by distant stages. The flow goes straight down the duct in x. Velocity only varies with height h. So it's a uniform along 2D duct of height h. This is tough. This is real tough. How to stream. So I mean, okay, let's clarify some definitions here, right? we're gonna go back right here. We're gonna ask, right? In this problem, consider a long duct of height h 2h is shown below. So I think this picture is important too. Y is equal 2h. So 1h above, 1h below. Got it. It's gonna show long duct. It's shown below. Got it. 3 velocity fields. So I mean, you know, what is a velocity field, right? Velocity fields tells you the velocity of the fluid at every point in space and time. Formally, it's a vector function. Okay, I like vector functions. So, I mean, yeah, so part of this is also, you know, linear algebra. Vector notation. U is the velocity of the x direction, y or v in the y direction, w in the z direction. So instead of one single speed, it's like having a map showing how fast and in one direction the fluid moves at every point in your duct. It's simplified to this, and that is because it explicitly says that, does it? I wonder how they drew that conclusion. So let me just double check what they're replacing here. uv goes into v is equal to 0, w is equal to... That's not what I'm looking for. Velocity at every point in space and time. U is the velocity in the x direction. Where is it simplified to that? Okay, that makes sense. And let me just remember this. How is change of position? Okay, I knew that. Dx dt, great. So if particle moves from track each, so we define it. We can't track each molecule. Right, makes sense. How do we find that in practice? It depends on what we know. Forget that in your duct pro. So awesome. So, I mean, off the rip here, let's just see. This is something that I really, really wanted to do, but I mean, so fart. I didn't even mean to. So this feature. So check it out. The honest truth is like, I mean, obviously I'm pretty novice to whatever skills this is testing, but I mean, I've asked questions that kind of get disorganized as we go along. So I think it's pretty rough. Let's just see if we can. Let's see if we can be very explicit with it. Explain. If I'm an extreme beginner. I like that. What happens? So let's just read the question again. I'm trying to consider log duct or uniform flow. Okay, we assume that the other velocity components are zero. We assume that the other velocity components, I don't even know what components are uniform flow is represented. Reynolds numbers. Got it. And also, matter of fact, let's get those solutions. Because they better have solutions, please. Oh, I want to do. This is in 2005, it would look like. Fine. We'll still tag it. We'll still tackle problem one because there's only one. We assume it's the other. Long flat tunnel, that's your duct. And air flowing through at the top and bottom are flat plates and the fluid moves forward between them. Okay. Sliding past one another. Cool. Each layer might move at a different speed. Interesting. Describe this using the velocity field. How fast each layer is moving. Okay. Distance down the duct. Why? Out of the page. Oh, okay. Because it's a 2D. Okay, that makes sense. Each layer moves at the same speed. Okay, got it. Like a moving walkway, everything's fast. Like a moving walkway. I don't understand that. 3 Ks in this problem. Okay, got the Kuwait flow. Oh my god, okay. I feel slower, but I got it. I felt slow not doing the top wall moves at speed. Okay, so let's just see what equations they had here. UW, where does this happen? The top will move at speed is fixed, and they mentioned that, right? Is the laminar flow that results when the upper wall is moving and the bottom wall is stationary. Okay, makes sense. Layer slides smoothly past each other. Okay, gotcha. So I mean, let's just go right back to the problem. And the bottom wall is stationary. Boom. There's the laminar flow. So I mean, they use that term laminar flow. What is? Like a deck of honey or syrup. Okay, the opposite term. What is high? Yeah, okay. Also, what did it just say right there? So I mean, it's a good question. Let me just see if I can figure it out first. Like I just want to apply myself. Just make sure I'm following up on this right here. This is insane. My brain is smushed. I will be 100% honest with you. I need to definitely sharpen up here. What was my question? Why does the flow depend only on height? Yeah, it's a very fair question. Let's say what's the duct? What the duct looks like. So imagine two big flat plates, one on top, one on another, forming a narrow tunnel. The duct fluid moves along the tunnel in the x direction. X is the direction the fluid moves. Y, the height. Yeah. Z into out of the pipe. Okay, we're ignoring that. It's 2D, right? What makes a fluid move? Top wall could be moving in the case of a Coué flow. Am I just saying that? Also, what is a pronunciation? Pronunciation. Coué? That's my guess.
You are looking at Julian's pronunciation guide, where we look at how to pronounce better some of the most mispronounced words
just tell
in
me
the
how to
world.
pronounce it,
Like,
brother.
break it down.
No.
Quetta.
Brother.
Quetta.
Okay, fine. I'm not saying that. I'm just saying Couette. I'm joking. Couette. Let's be classy. Couette. The Couette flow. Couette flow. I have something to talk about tomorrow. What am I gonna learn about fluid dynamics, bro? I'm just like, what does that even have to do with making rocket go in air? I'm sure it actually has a lot. I know. There's a trigger warning right there. I should have just said that right there. Why velocity changes with height? Okay. So top and bottom. I knew. Oh no, we're losing the plot here. The pressure difference could push the fluid forward. So yeah, let me just read into that again. The Couette flow is a laminar flow. The upper wall is moving at velocity. I can't imagine what is a duct. Okay, no, I understand. Okay, and the bottom wall is stationary. When a pressure drop is applied from end to end. Which ends, man? That's the top wall could be moving. A pressure difference could push the fluid forward. Okay, fine. Like along the duct, x direction. The walls at top and bottom cause friction. The friction slows down the layer near each wall, while the layers in the middle can move faster. So the speed changes as you move up or down in Y because the bottom and top layers feel the walls more. But as fixed height, well, once again, come on, we got this. So the speed changes as you move up or down. Speed changes as you move up or down and why, because the bottom and top layers feel the walls more. Feel the walls more. So okay, makes sense? Well, layers in the middle. Oh, okay. Okay, simple analogy. Picture traffic. Oh, I love it. Give me an example. Picture traffic in a long straight tunnel. The tunnel walls, traffic in a long straight tunnel walls rub against the side. Okay, the cars in the middle lane goes back on the changes along the length. That's exactly what's happening here. I like that example. That actually clarified a lot in my brain. Okay, so back. By the way, look here. I think the the organization is getting a little bit funky. I mean, look at this. I can ask it to redo stuff, but anyways, I think a little bit of organization matters. What does laminar flow? No, even more back. Explains to me as about an extreme bearing. Yes, that's what I want. Speed changes as you go up or down and why from. I like that. Two-way flow. Understood. I understood all this now. Both walls are fixed in the fluid. Faster in the center. Faster in the center. Gotcha. So there's a pressure pushing the fluid through. Cool. Gotcha. What are the question asks? So yeah, I mean, let's see. For all the velocity distributions, sketch the streamlines. So let me just go ahead and see if I can get a solid. I would also like a solution file. I think that would have been probably helpful. So what is this? Fall 25 homework assignment 1 solutions. So, solutions. So I think this is what I want. Is that what I want? It's not. So I mean, let's just knock out one with what they got. So draw streamlines. I think. So if I'm understanding this correctly, the uniform one. It's yeah. I mean, I get that. Show the path, the fluid layers. Well, they're flat lines here since flow only moves in X, yeah? Then, so let's go A. I understand that. Okay, great. Let me just go to OBS and just, y'all can see my streamline drawing. Wow, streamlines, great. Let's see part 2 here. Oh, look who's here. Cool. That's my girl right there. Showing love. Draw streamlines. Okay. Find vorticity. I love vorticity. What is a vorticity? You know? What is vorticity? Fair question, you know? quite visual once you get a vorticity plane definition. Vorticity measures how much the fluid is spinning around a point. Okay, think of it as how fast and in what direction the little fluid elements are rotating. So, okay, just make a tiny leaf or stick in the flow. If the flow just slides straight, the leaf moves forward, no spin. Flow twists around, the leaf spins in place. Local spinning motion. Okay, okay. So there's some equations here for vorticity. Gotcha. In your duct flow, so vorticity is equal to. So let me get my Greeks on too. I wonder. I mean, is that derivative? Yeah, partial derivative. Got it. Okay, partial derivative of v with respect to x minus. Got it. Okay, so in your duct flow, no vertical velocity, agreed. Only changes with height. Okay, so derivative of nothing minus the derivative of that. Derivative of, yeah, u with the, okay. So got you. So that means the vorticity comes directly. Oh, is that literally the answer? Okay. Let me just make sure I grill that in my noggin. Where is my, here it is. So let's go. Bang. B vorticity. Where? So disorganized. There's gotta be an easier way to do this. Scale issue, right? For 2D flows, vorticity. For 2D flows. So I mean, I get it. Let me just make sure that I have a good little workflow here and I understand this correctly. So vorticity is delta v over delta x, just x and y direction. So okay, in a 2D flow, that's what it is. That's what I really need to keep in mind here. Out of curiosity, you know what? Let me keep my my brain focused here. Vorticity is, I like that symbol. V minus a u over boom x over okay, that's good. That's good. I understand that because it is it's literally going from left to right. No, it's only dependent on x. There is no vertical velocity. In your duct flow, there is no vertical. Yeah, there's no vertical velocity, of course, because it's only flowing in the x direction. I get that. U is equal to u, y only changes with the height. Yeah, understood. So let's just make sure I got all my moving parts down here. And we'll do a little review. I know how long have I been streaming for actually? Is there a place I can see? Yeah, maybe right here I can see it, right? So I'm here for an hour. That's good. That's good. There's some solid work right here. Delta V minus delta U over delta X delta Y. Okay, good. We'll do a couple hours. How about that? We'll do 1 more hour of this. Yeah, it's a good idea. This is not what I want. What this symbol means. I knew what that told me. See, I need to find my way back up to the relevant areas because, I mean, that's what I'm looking for. So I'm just gonna pull up the assignment on this page, or I'll just do it here because I'm documenting all this. Oh, also, man, what is that? What is the Reynolds number? Most important ideas in all of fluid mechanics. I'm learning fluid mechanics, and it ties together almost everything you've been learning so far. Cool. Let's see how smooth or chaotic a flow will be. It compares two competing effects. Okay, you know what? Do myself a favor before we do that. We're gonna make sure that we have really good command. So. Constant. Uniform flow, because they explicitly defined RU. UI. Okay, got it. Now the Couette flow, it changes linearly because, or the Couette flow is it's moving linearly because it's only dependent on the upper wall moving at the constant velocity. The bottom wall is stationary, so that's why it's linear, because it's only dependent on one variable. I believe that's the correct. Curved. And yeah, let me remind myself what the vorticity is. So it's like how much the fluid is spinning around a point. So how fast and in what direction is little fluid elements rotating. So I'm gonna just think about it as I leave. So I'm gonna grill this down for me. 2D flow, it's calculated like that. I'm just gonna make this very ROM friendly. Two-D flow, V equals 0. Okay, fire. So we're talking about Reynolds numbers here. That's not what I'm looking for. Okay, so I have a kind of decent understanding of part A and part B. Okay, for all the velocities. Irrotational. So let me see if I can answer that myself. Flows are rotational or irrotational. So, I mean, where's that chart? So in the case of uniform, obviously it goes. It's rotational. Let me just see what they explicitly said here. Does the fluid rotate or just slide smoothly? So irrotational for a uniform, right? Let's see. rotational, if its vorticity is 0 everywhere. So in uniform, oh, I see. Okay, so basically rotational and irrotational just means if the vorticity, irrotational means if vorticity is 0 everywhere. Rotational means if vorticity is non-zero anywhere. Non-zero anywhere. Okay, understood. 2D ducts. Is this W? The W is vorticity, right? So for 2D ducts. Whenever we chug U infinite, when it's constant like that, obviously everywhere. Yep, makes sense. So for a QA, it's rotational. Did I get that correct? Yeah, okay. Velocity is blah, 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 blah. It's constant, not 0, so. Now the reason we're doing it is because we're calculating the vorticity first, and then is equal to negative that is also constant and not 0. Understood. The fluid layers are rotating at a steady rate. Okay. So I gotta be able to explain this tomorrow. Yeah, that makes sense. And then D is obviously because the two walls are moving. I mean, I can just visualize it. We can do it mathematically though. Like if I took the derivative of this, which I mean I can have it explained to me, but I mean we already calculated the vorticity earlier. And it was non-zero. It was dependent. What did it just say here? Not the Coué flow. I need the Puzuel. You know what? We also got to find out how to pronounce this. That is insane. I don't want to be. Poisoy. Whoa. Poisoya. And Poisoya. I'm just going to say Poisoy. Poisoy. Slope is equal to varies with y and 0. Only at non-zero elsewhere. Understood. Okay. Got you. So, okay, fine. So we got a solid understanding of, let me just get that down. Now we got strain rates. We got strain rates. The rate of deformation, think how is a tiny fluid square changing shape right now? Oh, deformation, I said deformation. The definitions for velocity. Okay, so it's a very explicit example, so we just got partial. Because V is equal to W is equal to, okay. Slow down here, slow down. Explain this to me like I'm a baby. No, extreme. Extreme novice. Tiny square inside the flowing fluid is the square might stay the same shape. Stretch or switch. Tilt like a diamond. Stretch or squidge. So I guess that's like one way. One second here. My head is splitting. This is what happens when you just like jump into some very hard stuff. It's been a minute since I'm not. This is gibberish to me. A lot of it's a little square, but I'm getting it slowly. So that's the good news. I'll do a good review after. Maybe I'm even gonna. I think I'm gonna probably design something cool here. Slanted, a little square fluid if top edge gets pulled. Man, that's crazy to think about that they like actually broke this down like so hard. Like it's blowing my mind. I'm very very inspired by people who are actually like good at this stuff. So okay, we look at how the speed we go up in height y. That's written as understood that. And what was the explicit definition we have right here? 1/2 of this ij, the change in. So yeah, this was kind of bothering me. I don't. I need to. Z direction. Duh. Oof. Okay. I derped. V equals W equals 0. And it only depends on Y. Understood. Yeah. Okay. Normal. External. Normal strain rates. For double Y. So it's taken at 2 points because the subscripts for strain rate, why are they 2? I need to really. So one part of the velocity changes when there. One part of the velocity changes positions. So now it's just throwing me off. So we need 2 labels. Subscripts. Each stand for a direction. Okay, I'm not gonna lie. I can confidently say that this has thrown me. This has thrown me for a loop. That's okay. I knew it was gonna be hard, so It's hard. It's hard for sure. Let's go. That's not what I'm looking for. Let's go. I mean, it even told me, and I mean, it's so dense that sometimes there's no problem asking again and again and again. So this is, let me just take a really quick objective step back and show you how, like, great the information is. Don't get me wrong, but maybe lost in translation, unless you're very disciplined about how you're going about this. Like, I'm talking. Like, you're constantly doing reviews and you're just trained in the art of prompting. Like, I'm sure that's going to be a very important skill that's going to probably be taught. I mean, you get lost in translation. Like, like look at all of this. Like, you can ask for follow-ups, but unless you're very strategic with, that's not what I want. Unless you're very strategic, oh, that's interesting actually. I think oh no. I thought it responds to the messages through like explicit code lines, and it just shows you that. But unless you're very strategic with like your workflow and you know exactly how you're doing it, and it's not just like you're trying to get through new and challenging skills like this. Like, if you're not doing that, or rather when you are trying to get through new and challenging skills, if you have a good workflow, then it might be easier to use the state of the art tools to help you out. Otherwise, you're kind of just like in limbo. I mean, we can see this right now. Me personally, like, I'm gonna do myself a favor, and I understand, like, this is the work you got to put in. Like, this is what happens when you're a novice. I'm just very curious about like what exactly will make this easier. So I can clarify, like, here, just give me a summary of everything that I've asked for so far, and it's gonna be like, we'll do that in a sec. Matter of fact, but. Matter of fact, when I go through my review, I'm not gonna. If I started from the top and went through the bottom, like, I could see what my brain did. It might be frazzled because I feel like sometimes you can use ChatGPT as like a scratchbook, and you can be disciplined about that too. But kind of like a user-friendly issue right there. In this niche, like when you're self-learning stuff. So I just want to be very explicit about that. So let's get this down, because this is throwing me off. This is throwing me for a spin right here. Flows are rotational. So I'm really glad. I think I really do understand this in the case of this 2D duct flow with height 2h. Otherwise, yeah. Give me one second. I gotta use the restroom. let's get back to it. Let's go to OBS. Cool, I love it. One viewer, just me, myself, and I. Let's go. I don't know why I checked that. I knew that was going to be the case. Okay, right, zero strain rate, right? Start me over. So, I mean, this is obviously a contentious thing for me. Did I even use it? Did I say that right? Contentious. I did not use that right. Something is shearing between layers. Only XY matters to the non-zero strain is this term. So small square of fluid floating in the flow, I get that. Move, drift forward is a whole little wheel turning. Fast. Okay, okay. I like that. I understand that. That's very straightforward. Think about your duct flow. Before, after some time. And the speed changes with height. Why is the top of your little square moves a bit faster than the bottom? Okay, okay, interesting. Got it. Shear strain rate. Okay, we describe Describe that mathematically. Yes, give it to me. So we measure the difference in speed between the top and bottom layers. If the speed U changes as a move up in height, why we say rate of change with height equals. That make okay. Wait. Okay, the speed. I get the rate of change with height. Okay, got it. It's basic shear strain. Depending on convention. Okay. What it means physically. If D tilt, no strain. Oh. Okay, clap it up. I get it. If du over dy is big, the speed changes a lot with height. Square tilts quickly. Understood. Step 5, why we care. Why do we care? Okay, let's test the intuition. Yeah, I like that. Let's test my intuition at the top. The spin, tilt, tilt. Yay. Let's go, the top of. Okay, good. So now for all the velocity, just calculate the strain rates. So 1/2 du over dy. So okay, let's go back to it. Compute the strain rate for each of the 3 flows. Yeah, I know. Figure out how much the flow layers are tilting or stretching in each type of flow. Our flow is 2D, got it. Fluid only moves forward, got it. Speed only changes with height, got it. So all the interesting shit. Key formula, right? Okay, 1I, how does what change with what? What is the rate of, I just said, come on, rate of change of speed over height. Okay, got it. Okay. So we're calculating 1/2 du. Okay, so I mean, let's just do du over dy. So I think it's important that we kind of calculate that. I'm gonna make a program here. With this constant that is understood. Derivative of a constant is 0, no strain. No tilt, understood that. This is also, this will just reduce to a number. Because it's a single equation. Okay, the Couette flow is messing with me a little bit here. Constant strain, every layer shares the same amount. I understand that whatever, at any given point, okay, let's just very confused. Somebody's gotta clap after you type that fast. Perfect. Let's top while moving right, got it. Fluid in between, no moving, yep, understood. What the velocity looks like, yep, they mentioned that. The key idea is the speed increase linearly with height h. Oh, because it's a linear, okay. The speed increases linearly with height h. That means, yeah, I get that. I get the the curve. Okay. I think I'm in analysis paralysis. I understand it's just like a linear equation, and the derivative of that with respect to y is constant strain rate. So I think that's literally what it's saying there. So I understand. Give me 1 sec here. Bro. Wow, 2 hours. It's been 2 hours. That has not flown by for me, I'm not gonna lie. Y'all thought I was about to be like, that was easy. That was too easy. It's not. This is not. This is brain splitting. I'm not gonna lie. But I got this. This is the thing. This is what we're doing. I forgot how to say that. What did they say? Poisson? Poisoy? Poisoy. 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 I look like such a nerd in the stream, bro. I look cooked. That's okay. I'm not trying to be a pretty boy no more. I'm getting distracted here, right? Okay, I understand that that's constant and that was like parabolic. So if, as far as strain rate goes, what was the distinction? So I understand it was tilt, spin, and still, right? Explain the Coe flow. Very confused. I understand the Coe flow now. I think I made sense of it. Variable strain rate, yeah. Because we said... That makes sense. Let me see if I can explain this just for my own understanding. So the middle is what, or because there's friction on both layers and the fluid moves the fastest in the middle, the curve of speed as you go from like top to bottom is kind of like a parabola. So like that rate of change is parabolic. So that means that the derivative of that is just linear. So variable rate of change. So I mean, what does that actually mean? So does that mean that it gets top wall? So no, I'm not looking for the Coe flow. Variable strain rate here. Strongest strain, the biggest strain is near the walls. Yeah, okay. Layers near the wall tilt more because, okay, what was the, yeah, okay. I understand it. It's either tilt or no tilt. Is that correct? Let me just clarify something. With the what was it? Puzzle something? Come on, man. With the okay, let's just do one of these. That did not work. With the layers near the walls, spin and not tilt. Man, I don't like that. It's just so nice to me sometimes. I'm like, you really want to just make me feel better. And I'm like, I know it's a funny setup. I just seen the memes about it, right? I'm like, I actually appreciate it. I'm not lying. This is a dysfunctional relationship. Like a parabola. I understand this. Okay, middle layers, blah, 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 blah. They're shearing. Okay, they're shearing. I don't even think I was using the right terminology. Let me just clarify that. What are the different types of was talking about strain rates. Then they talked about shear, like shear. Come on. Yo, thank you. That's what I'm saying. That's what I've been saying the entire time. I'm a real fluid dynamicist. I think I said that correctly. Dynamicist. You feel me? Strain rate. Stretching or squeezing. Tilting or sliding. Stretching or squeezing. Oh, that's right. So it can do three things. It can just be uniform. It can tilt or slide. Or it could stretch. Oh, no, sorry. It could stretch and squeeze. Or it could tilt and slide. Did I get that correct? Becomes a diamond shape. Okay. Got you. Normal strain happens. I think I understand. It's just 1/2 du over dx, or du over dy, rate of speed as with respects to height, and there was actually an interesting section there, what actually physically happens. So what's going on here? No shearing, the fluid stays rigid, understood. Steady, even tilting everywhere, understood. Near the wall tilt more, understood. Okay. That's good enough, let me write it down. Let's get a little review. Okay, I'm just gonna do it mathematically. It's just the easiest way. I do wanna make it make sense in my head too, but you know, for ease, this is a 2005 problem, man. Like I'm sure, I'm pretty sure. Pretty sure that it's gonna be. Let's go right here. What was it? 1/2 du. Well, is that specific? Was that specific to a 2D duct? That shear? So I was so distracted. Something else is going on over here. Let's do it like that. So I guess it's for symbols. This is the full strain rate tensor. I think it just simplified it for me, so I'll explore this. So I mean, this is for what? Simple 2D flow, so we can just use du over dy. In your duct flow, u is changing with height. V is constantly 0, w, z direction is 0. Understood that. So close to being done with this. All right, let's call that like somewhat understood. This is really, this isn't even the surface of rocket science. Consider a slice of the fluid between, for all of the, okay, slices, that's tough. Velocity, calculate the, okay, explain it to me. Let's go. Party. Okay, okay. That's not what I'm looking for. Okay, here. Acceleration of a fluid parcel, the material derivative. Stop it. Lost. Explain like I'm a beginner. I'm a complete novice, which I am. Understood. That's what acceleration, I understand that. Each tiny piece of fluid. Yeah, okay. Bottom layer moves slower. Middle layer moves fast. Gotcha. That makes sense. The formula for acceleration in fluids is okay. I like it. It's total acceleration change over time plus change due to motion in fluids. Acceleration in fluids. Okay. Change due to motion. Okay, I like that it assured me here because I was lost. Sorry, I got distracted there. Convective term, my friend, I don't understand. I like this more intuitive explanation a lot more. Does a flow speed change over time? Yeah, I guess it. So I like this intuition right here. So the flow is steady, so the first part is 0. I understand this. Okay, each fluid stays in its own layer, no up or down motion. Means it doesn't move into faster or slow regions, it just glides forward. So the second part is also 0. Changes due to motion. Each fluid particle stays in its own layer. So, I mean, let's see what this always gets. So this is a really, I need to brush up on this. I feel like I have an easier time just breaking it down into formulas, but I mean, in this case, the intuition kind of makes sense. So the first component becomes conclusion. All terms vanish. Du over dt is equal to 0. I understand what this right here does. If this is the symbol, if it's just change over time, change due to motion. So okay, let me just write the intuitive example. I need to know how to like apply this. Acceleration, was that specifically acceleration of fluids, right? Acceleration in fluids. Okay, I mean, I got an intuitive understanding of the ducts here, and so it's just like 0 across the board, I guess. Let me just double check that. Yeah, understood. Consider a slice of the fluid between here and here. Okay, so I'm gonna do myself a favor. I think we're at a couple hours. So I think I'm gonna go follow this up, or not follow this up. I'm gonna go study this, or I'm gonna go review this because I think it's very dense with information. I had a lot of interesting learnings here today. At a high level, like what's gonna happen here is with the streams, I'm gonna learn more about. I mean, obviously the explicit. I'm gonna learn more about rocket science, but in the time out of the stream, I gotta think about like, I gotta be more optical about like what just happened. So probably just, think about what's happening with, what would have made it easier for me to learn that. I think one very clear thing we have here is. This feels like a chat, like a little bit disorganized for me. So maybe I could have broke it down into different components, like meaning like a different chat for a different like if I wanted to if I just wanted some definitions. Maybe a different chat for that, but yeah, I think the overlap between like actually asking it real like relevant questions and just asking it like a random little like scratchbook thought. I think it's just like all in the same place. So maybe that's like a conscious thing. Maybe there are some very like. I'm sure there are some very disciplined users of GPTs, of LLMs. So, I don't know. It's something to think about. But I mean, that was fun. We'll probably run this again tomorrow, so that'll be great. Okay.